What if you could capture an object, not just as a flat picture, but in its full, three-dimensional glory? Imagine holding a transparent plate up to the light and seeing a perfect, ghostly chess piece floating in space. An image you could walk around and view from different angles, just as if the real object were there. This isn't science fiction, it's the remarkable reality of holography. It's a method of recording an entire light field, a complete wavefront of light as it reflects off an object. A photograph only captures the intensity of light, how bright or dark each point is. A hologram captures both the intensity and the phase of the light waves. This preservation of phase information is the absolute key to everything. Phase tells us about the depth and position of each point on the object, like listening to a full symphony in a concert hall versus hearing a single piano note. The photograph is that single note, clear but flat. The hologram is the full symphony, every instrument from its place on stage, creating a spatial experience. By recording this complete information, a hologram allows us to reconstruct the light field itself. Illuminate a holographic plate and you recreate the original light waves, fooling your eyes and brain into seeing it in 3 dimensions. For an electrical engineer, this concept should be electrifying. We spend our careers manipulating waves, electromagnetic waves. Light is another part of the electromagnetic spectrum, with much higher frequency and shorter wavelength. Understanding how to record and reconstruct these light waves extends principles you already use every day. It's about encoding complex information onto a medium, encoding digital data onto a magnetic disk, or onto a flash memory chip. Holography instead encodes the physical properties of light onto a special photographic plate. To truly grasp holography, we must first think about the nature of light itself. Light behaves as a wave, much like ripples on a pond. Now, imagine 2 sets of ripples meeting. Where 2 peaks meet, they combine to create a much larger peak. This is called constructive interference. Where a peak meets a trough, they cancel each other out, leaving the water flat. This is destructive interference. This beautiful dance of waves, reinforcement and cancellation, is called an interference pattern. It's a fundamental property of all waves and the bedrock of holography. However, not just any light will do. The light from a standard light bulb is a chaotic jumble of waves of different frequencies and phases, all out of step with one another. It's like a crowd of people all shouting at once, a noisy, incoherent mess. To create the clean, orderly interference pattern needed for a hologram, you need a special kind of light. You need coherent light. This is where the laser comes in. A laser produces a beam of light where all the waves are of a single color or wavelength. Creating a hologram is a process that demands incredible precision, almost like performing delicate surgery on light itself. The first practical step is to create an environment of absolute stability. Because we are recording an interference pattern with details smaller than the wavelength of light, even the slightest vibration can ruin the entire recording. A person walking in the next room, a gentle breeze from a vent, or even the subtle rumble of distant traffic. For this reason, holography is almost always performed on a heavy, vibration-dampening optical table, often in a darkened room to prevent stray light from interfering. Next, you need to set up the optics. The process begins with a laser. The laser beam is directed into a beam splitter, typically a partially silvered mirror. It splits the single laser beam into 2 identical coherent beams. One becomes the reference beam, the other becomes the object beam. Each of these beams is then passed through a diverging lens, which spreads the narrow beam out to illuminate a wider area, much like a flashlight beam spreading out from its source. Meticulous alignment using a series of mirrors is crucial to direct these beams precisely where they need to go. The object beam is carefully aimed to completely illuminate the subject of the hologram. The light reflects off the object's surface, its waves altered, picking up the 3-dimensional information of the object's form. This scattered light then travels towards the recording medium. So, the story of holography actually begins not with a sudden inspiration about 3D images, but with a quest to improve electron microscopes. 1947, Denis Gabor, working to correct spherical aberration in electron microscopes. He theorized using a coherent electron beam to record an interference pattern, a hologram. Holos, meaning whole grammar, meaning message, illuminate that pattern to reconstruct a corrected image. Revolutionary, but ahead of its time. No coherent light source then. Gabor's holograms were faint and distorted. For a decade, his work sat as an impractical curiosity. 1960. Theodore Maiman invents the laser. The laser equal sign intense, coherent light Gabor needed. Early 1960s, Emmett Leith and Uris Upatnieks revisit Gabor. They realize the laser is the missing piece. They use an off-axis technique, reference beam, object beam, arriving at different angles to avoid overlap. Result? The first clear transmission holograms that create ghostly 3D images with a laser. For today's electrical engineer, holography is far from an optical curiosity. It's a powerful tool with profound practical applications. One of the most significant is data storage. A holographic storage system can record data not just on a surface, but throughout the entire volume of a crystal or polymer. By superimposing multiple holograms in the same volume, each at a slightly different angle, a single small disk could hold terabytes of information. This offers a potential solution for massive data archiving needs, promising storage densities and transfer rates far exceeding current tech. Understanding holography gives engineers a deeper appreciation for wave-based phenomena central to modern technology. Don't forget to like, share and subscribe, ET Muster.